Okay, cool guys. Yeah, I'm Carter. I'm the CEO of QED. So today we're going to be talking a little bit about how QED's state model works and how we're able to horizontally scale our blockchain. So just a little bit about me really briefly. So I come more from the security and reverse engineering community. I also ran proof of stake infrastructure for a bunch of POS chains, specifically EOS. We were a top 21 block producer for quite a few years, processed 150 million transactions in unique transactions in production. So we've been building blockchain infrastructure as well. I also built ModP, which is a Minecraft Pocket Edition, mobile version of Minecraft modding engine. We had over 150,000 developers in our community and over 20 million installs across Android and iOS. So touched a little bit in the Web 2 ecosystem with that. But let's talk about serial and scaling and horizontal scaling and parallel processing in general as far as it goes with the L2 space. I'm sure a lot of you guys here are familiar with L2 beat, probably. Yeah. So right now, if we look at L2s, we are able to process more transactions than Ethereum alone could, but it's not some exponential growth curve. We're not saying oh, suddenly all of our blockchain scaling problems are solved. I can build Twitter on Ethereum, right? This has not happened. And we're even low 1 digits. And you can probably also see a lot of these guys are optimistic rollups that do not have fraud proofs, which is a little bit sketchy. But yeah, so with non-ZK projects, it makes a lot of sense to have serial execution because every node needs to check the results of every other node, and if one Ethereum node detects that a transaction was let's say failed, report has a certain state. If another Ethereum node wants to know that this state should be as it is, they have to actually execute those transactions. So if you want to build an L1 where you have lots and lots of people running full nodes, then the actual sort of requirements to run the full node needs to be sufficiently low so that you can have lots of people running full nodes. Because as soon as you try to, even if you build a parallel state model with an L1, let's say I need a whole data center of computers to run all of the parallel transactions, right? Not many people would run full nodes in that situation because it would be prohibitively costly, right? So there's this with non-ZK L1s, there's this big trade-off where you don't even want the performance to be that fast because then it makes it harder to run a full node. And then you become less decentralized, which is the whole point why we did this in the first place, right? So adding more nodes doesn't increase TPS. It actually kind of lowers it a little bit because we have to make sure that everyone can keep up. But yeah, the reason why blockchains are serial, I'm sure most of the people here are kind of more familiar with this. We have race conditions, right? I have two transactions that try to access the same state slot. You can imagine, if I send money to two different people and then someone also sends money to me at the same time, the rights that we're making to my balances in an ERC20 contract are not atomic. So, everyone, each of these transactions, if we run them in serial, it will operate correctly. But if we run them in parallel, each of them have different results about what the end contract state should be. So yeah, because of this race condition, you can't really parallelize. Some projects have tried to do workarounds, basically checking to see roughly which state slots each transaction is doing. And then later, so first I execute them all in parallel, and then I see if there's any conflicts and then retry again. There have been a few attempts in this area. You could also try to use some sort of modern ACID database principles to try to do it, but no one's really figured it out. It hasn't really worked. So yeah, but then there's of course the questions can we do better than this? Because right now the limiting factor on blockchain usage is just that transaction space is scarce, and that's why transactions are expensive, right? Bidding for gas is the reason why you have to pay. So is there any better that we can do than this? And the answer is yes. So so we have a new state model that we use on QED. Specifically for each user, we have a separate contract state tree for the given user. So you can imagine if there's a token contract, every user will have a separate state tree for that token contract. And then we have a tree which contains the specifically the hash of verifier data for a bunch of zero-knowledge circuits that are allowed to authenticate updates to each of the contract trees. And then as a user, when I'm transacting, I'm able to read from the other users' contract state trees as they were at the end of the previous block, so when they're already finalized, but I'm only able to write to my own. So you can imagine that a transfer looks something like I burn X number of tokens in Tony's name, and then in the next block, Tony can prove that, oh, I've burned these tokens in his name, and he can now mint them for himself. So we also have multi-user interactions. So we have a thing called covenants. The way that works is essentially I say, okay, if I burn these tokens for you, and if you claim them, you must also do these 3 transactions, right? So we can still have these sort of complex multi-user interactions. We also have some bot users that allow us to do also pretty inherently serial things like build AMMs and order books, but this is just kind of a little bit of an overview there. But yeah, because we've separated the users, what users are able to write to, yeah, we can batch, or we can rather, yeah, let me just show you the animation. Yeah, so users prove their transactions locally because we know for a fact that no one else can write to their user's state tree. Since it's confined to themselves. So the users prove a state transition on specifically this node here. So you can imagine that each user has one tree of trees, and each of the subtrees is a contract state tree. And so as a user, what I'm locally proving is that my contract state tree's root has transitioned from certain root to a new root, right? And then I generate a series of proofs. Each of these proofs are going to recursively verify a contract function proof that's defined by your original function. The proofs that are allowed to be used to authenticate contract state tree roots to be updated are stored in the leaves of this contract function tree. So you can imagine we have over here a circuit which is going to recursively verify that contract function proof, which shows that, okay, this contract state tree has mutated from a certain state to a new state. And this is this circuit here is also going to check to ensure that that proof's verifier data is in the white, the whitelist tree, or the hash of the verifier data is in the whitelist tree for that particular contract. So if we're trying to modify the nth contract state tree's root for a user, we also must have a proof along with it that has verifier data which is in the nth, that is in the nth contract function tree. So these leaves index the contracts for their specific whitelists, and then these leaves index the contracts for the users. Index 1 in one tree is the same as index 1 in another tree. So yeah. And then we eventually generate a single proof of all of those different transforms that I've done on the user's state root, and we end up with a succinct NCAP proof that basically shows, okay, this user's state root has legally transitioned from state root A to state root B, and then we send the proofs off to the network. So each user has one proof, no matter how many transactions they've done. We send that proof along with all of their state deltas to our decentralized proving network. Decentralized proving network are going to do a series of 4-to-1 operations. In the animation, it's doing 2-to-1, but you can imagine you have one proof which recursively verifies 2 proofs along with associated with delta Merkle proofs that prove the, in the case of it being just the NCAPs from the users leaf roots, or the leaves over here. So you can imagine this is all of the users in the chain, right? We first have a proof that takes these 2 users' proofs along with the delta Merkle proofs that link them to their nearest common ancestor Merkle cap. And we verify the proofs and then generate a new proof which proves up to a certain Merkle cap. And then we can continue to do this process for all of the users in the block until we have one succinct proof for all of the transactions that occurred in the block. And the great thing is we can do this process in parallel. Specifically, we get block times of O of log base 4 of n. And the 4-to-1 proof process takes 400 milliseconds. So you can do 1 million users in 6 seconds. And we've done this on AWS, and it works. So we're very happy about that. But yeah, so you can scale it quite easily. Proof size, 30 kilobytes. Yeah, proving time is 0.35 seconds. And this is on my MacBook. We have an iPhone, we have mobile SDKs, right now only iOS, because we've partnered with a lot of game companies. We actually just announced our partnership. We're in the Unity accelerator, so hopefully some more official partnerships there. But yeah, Like on my laptop, which is an old M1, it's like 0.35 seconds. So yeah, if it takes like, let's say 0.1 second to send a 30 kilobyte proof to the next person, then yeah, you can get 223,000 TPS with 1 million people participating in the block. The other thing is, so we've separated our data availability miners from the provers, because in order for you to get these fast block times, you have to have a lot of provers, right? So the great thing is, like, we have data availability miners who are keeping the data available by just, they have like a random challenge where they have to prove like a certain random leaf within our larger state tree. They have to give a Merkle proof. Which index it is determined by like a pseudo-random number that's the same for everyone, and then they hash that along with their user ID. So we get like specifically for each user. But the great thing about that is that in order to prove your transactions locally and to participate in this 4-to-1 proving, you don't have to have a copy of the entire state tree. So you can do it on your phone, you can do it. The people that are submitting the transactions can also participate in the proving, and there's no like trust or you know, anything there's no like real there's no real like requirement to barrier to entry to participate. So yeah, we want normal people mining, not just the mining teams. The mining teams can do the data availability. But yeah, the great thing about that is we get 1 gas fee for unlimited transactions. Now you do have to pay for your state deltas. So you can imagine that if I am making a bunch of transactions which are mutating like the same few state slots, then I can save some money, right? But if I'm just adding more and more state slots, you still got to pay if you're storing a bunch of data to chain. But the actual number of transactions that you're running doesn't affect the price you pay, because the proof size is the same and you're proving it locally, so it just means that you're going to spend more time executing locally. But these contract function proofs, it takes like, generally these take about 80 milliseconds, and then these like double recursive proofs take like 190 to 200. But we're working on like improving our prover. But yeah, so like we're running like it's 100 bits of fry, so we're like we're trying to make everything very end-to-end secure. We could make things a lot faster if we took some shortcuts, but we know like we have to make sure that especially if we're not doing like centralized prover, that everything is a-okay up to spec. But yeah, so Vitalik actually recently at the Modular Summit showed this diagram, which was very reminiscent of what we're building. So we're very happy that more people are getting on the tree recursion bandwagon. But the real important thing is that in order to take advantage of this kind of parallel proving, you need to have a state model which matches the topology of your proving. So if you're proving in parallel, you want to make sure that at each step when I'm doing the recursive verification, I'm also doing an associated delta Merkle proof, and you need to design your state model around that. And that is like the cost of being horizontally scalable, is you need to have this like very hard state isolation. Otherwise, you would have to implement like that sort of back off logic that some of the other parallelizable blockchains are doing in ZK, which is probably not feasible. But you don't really need it. It's pretty easy to build applications. We also support, like, I know I've talked a lot, but yeah, like this just kind of goes through some of the things, how I think everyone pretty much gets the idea. I can show you guys how we build contracts. So we also support JavaScript, TypeScript, and Python. I can show you guys how like we can type up a real quick contract and compile to Circom or like a circuit diagram if you guys are curious. I don't know, like, I've talked a lot, I apologize. Ha ha ha. We have programmable public key cryptography, so public keys on QED are actually, it's like the hash of verifier data for some arbitrary circuit. And then when I want to give a signature, I just have to generate a proof which has public inputs that correspond to like the message that I'm signing, as well as some contextual information about the state of the chain. Great thing with that is that, if I want to make it QED compatible with Ethereum signatures, I just write an SCP 256K1 verifier in my circuit, right? Verify, in order to like sign transactions on QED, I need to provide a Ethereum signature for this, let's say public key, right? But you can also make like bot users, lots of fun stuff. This kind of goes into random things. Yeah, does anyone have any questions? Do you want to see a JavaScript contract?
Yeah, we can just see that and then jump to questions.
Okay, cool. So here we have some like voting tally. Maybe we should make something a little bit simpler. So over here we have like an ABI format that we use to define like the state and all the functions for the contract, because we support JavaScript and Python and hopefully more languages in the future. So there needs to be some kind of common calling convention in state layout formatting. Actually, we can see an example over here of like what like your state definition can look like. So you can imagine that we have some functions, and yeah, we can like address different, it basically takes like some state structure and converts it into the minimum bounding Merkle tree, so that for any, like, this is what's used for the programming languages when I do like this dot state dot something dot something, it converts it into like a Merkle lookup, right? So yeah, anyways, I can make just really quickly. Okay, so yeah, so here we have a simple voting contract. It takes in like some different votes, and it's going to output a result. So if you see, like, if I go over here, let's remove this constraint for now. I can go age, I don't know, 28, 1, 29, 22, 12. If I go over here and I click compile contracts, I can then call, so we can, like, you know, test out the contract in the browser, much the same as something like Remix. However, we also support like browser debugging. So I can go in here, and as we can see, like right now the results, it's, I don't know if you guys can see it clearly enough. I guess you can. We can, like, you know, I know like for a lot of Web 2 developers, this may seem quite normal, but if you've ever tried to debug a Solidity contract, you probably know that the Solidity debugging experience is subpar. Yeah, so we have debugger. In addition, we can generate a like circuit diagram for this particular. This is going to be a big circuit diagram. But this just shows like the arithmetization for our JavaScript code. Maybe I should make a simpler one so that we can see exactly like what's going on. Give me a second. Compile. All right. Let's see, what are we returning? Some result. Let's change this. Let's have one output. Okay. Let's just make sure this is working. Should return 1 if I do that. Okay, so I can do something like, I don't know, let's say let sum equals 0, I don't know, numbers dot for each x, I don't know, like sum plus or equals x, and then I can return sum. And if we then compile and generate a nice circuit diagram, we can see what's going on. So as you can see, it's summing up the numbers, right? We can also generate like circum code. I can make it more complex. Like, let's say I want to do, I don't know, like some function, hello, I don't know. Turn, I don't know, x times y plus 3, or let's say like, I don't know, if x equals, let's just make it simple for now. Compile, I don't know, hello, x, 1, 2, 3, if I compile and click LaTeX circuit diagram, as you can see, yeah. So it can handle like very, very complex, like, you know, JavaScript programs. It's anything that works in ES6 that's not non-deterministic, we currently support. So like the ECMA script, like main unit tests are working. We don't support floating points right now, but all of the ECMA, like script official unit tests that aren't floating point or non-deterministic are currently running. For JavaScript functions, like you can imagine you have a for loop where the number of iterations is like is dependent on the number of, or is dependent on the inputs to the function. So you can imagine like, I have some function which takes an input of x, and for, you know, I equals 0, like k is, or I is less than x, we would have an indeterminate number of constraints. So for that, our like high-level constraint language actually allows us to have like loops in constraints. So you can imagine that it has some like notion of permuting a function or iterating a function on itself multiple times. So like for those kind of, I guess, if those features are used in our high-level constraint language, then we compile to like our own little VM that's written in Starkey. We also will very soon have MIDE VM bytecode support. So you can imagine that going through those constraints, you basically just like walk from the like, you do like a depth first walk of like one of these constraint trees in MIDE VM instructions, then you get the correct answer out the end. Yeah, for if you don't have any of those, then yeah, we compile, currently you can target R1CS, Plunky2, and CIRCOM, like generalized CIRCOM. So yeah, that's QED. I've talked a lot. If anyone has any questions, please let me know. Otherwise, yeah.
Sure, beautiful. And open up for questions, I guess.
Okay, yeah.
Just a quick question. You had a slide on Vitalik's ideal architecture for scalability blockchain. Could you maybe give a brief description of that? And
Sure.
How it compares to what you're doing?
So Vitalik didn't actually talk that much about the scaling end. He was more talking about having one succinct proof for all of the activity that has occurred, which we do implement. So at the end of a QED block, you get a single proof, which recursively verifies the previous block proof, and recursively verifies the proof from those user operations that took place. So you get all the transactions in the proof, as well as the contract deployments and external events that we register on QED. So yeah, but he wasn't necessarily saying that. Just for like full disclosure, he wasn't saying like, oh, you should use a state model that like mirrors the hierarchy of your proof tree. No, that's what we're doing. But yeah.
Yeah, I got one question.
Sure.
So I was wondering about the DA providers in QED. So
Yep.
basically, the way to verify that data is available in their node, I guess, is we give them like the very bottom leaf and ask them to return the result.
Exactly.
And then, but however, does that mean they cannot basically churn away historical data? So you basically have to keep whatever has been there.
So currently, the data availability nodes, their challenges are guaranteed to be from the past 10 blocks.
Okay.
And the reason why we do that is because technically, as a local prover, I don't have to be synced or proving a local proof chain that's synced to head, right? As long as I don't go backwards in time. So if in our diagram, I guess it's not there, we store like which is the last block that the user participated, and then there's also a nonce. So I don't have to know about the rest of the world technically at the current block.
Yeah, they're irrelevant.
But we would expect the users to upgrade to the latest head after some period of time, right?
Okay.
But giving that sort of flexibility of 10, like, allows users not to have to like quickly submit off their proof chains whenever a new block begins, right?
Okay, so basically we doesn't care about whatever happens before the previous 10 blocks.
I mean, you could. So we do have like a full history solution if you want it, but you don't have to. But for the data availability nodes, the main thing is like we have like a commit reveal process that generates a pseudo random number, and that's actually done by the people that are participating in like the actual like decentralized proving network. And so they end up with a pseudo random number via like commit reveal or hash commit reveal XOR, and then this like value is used. So you hash this value plus your user ID, and that generates the random number, which directs you to the correct challenge that you have to commit as a data availability miner. And you could not do the data availability mining task. You just don't get paid anything if you don't do it. So.
Yeah. I was wondering if we're able to implement something like the Litecoin for the data solutions, so that we can have a number of users checking on the data providers.
Probably could. Another thing that we're thinking. So this also comes up because let's say I'm local proving, right? I don't have a full copy of the state. Why will the data availability providers provide me this state information? Right now, it's like, why do Ethereum nodes give you like why do they respond with the correct answer, right? There may be some way to incentivize this behavior, or to have the portion of the user's final gas fee go to the person that provided them with proofs. Yeah, like once we launch our testnet, we're going to be exploring a lot of those things. But yeah, I mean, right now we just have them generate a zero knowledge proof that the Merkle, okay, I provided the correct Merkle proof with this pseudo random number. and then that's included as part of like the decentralized proving. So we all have like one group of people doing this like standardized task, which is nice. But yeah, there's definitely a lot of other approaches we could look at.
Yeah, definitely. So it seems like our data providers still be more like segregated, serving different users because different.
Correct.
One user only care about their own.
Yes.
State. They don't care about the entire.
Correct. Yeah. We're thinking about ways to work around that. Like you could apply like, I mean, you could swap every now and then, I guess, or as part of as you're moving up when you update, if two users next to each other like are on different branches, you could probably swap them over. I don't know. It would make things quite complicated, but if we have to, there are sort of ways to go about doing that. But then you have some consistency issues with like the way that the apps track users, like user ID so-and-so, which app ID does it actually map to? So yeah, food for thought. Yeah. Any other questions? Sorry for talking so long.
No worries. I guess we love that, and thank you, Carter.
Cool, thanks.